This video is brought to you by mywayteaching.com.
In this particular part, we are going to study about hydraulic machines. Okay. See, let us now see what happens when we change the pressure on a fluid which is contained in a vessel. Okay. You just consider a horizontal cylinder with a piston and three vertical tubes at different points. Okay, a horizontal cylinder with a piston and three vertical tubes at different points. The pressure in the horizontal cylinder is increased by the height of liquid column in vertical tubes. Okay, it is necessarily the same in all. If we push the piston, the fluid level rises in all the tubes, again reaching the same level in each one of them. Isn't it? Because that pressure of the fluid will be same for all the three tubes, so it reaches the same level. So this indicates that when pressure on the cylinder was increased, it was distributed uniformly throughout. We can say whenever external pressure is applied on any part of a fluid which is contained in a vessel, it is transmitted diminished and equally in all the directions. Okay, this is the Pascal's law for transmission of fluid pressure, and it has many applications even in our day to day life. Okay, here we have considered the example of a vessel with three tubes. When the that vessel, the fluid in the fluid in the vessel, whenever we increase the pressure of the fluid in the vessel, that pressure is uniformly distributed throughout the vessel. Okay, so that the height of the fluid in each of those three tubes will be same, because that pressure of that fluid is same for all, isn't it? So that's what the Pascal law for transmission of fluid pressure says. Okay, when an external pressure is applied on any part of the fluid in a vessel, then it is transmitted undiminished and equally in all the directions. Okay, a number of devices such as hydraulic lift and hydraulic brakes are based on this law only. Okay, hydraulic lift and hydraulic brake. Okay, these depend on the Pascal's law. They work on the Pascal law. Okay, in these devices, fluids are used for transmitting pressure, because in fluid the pressure is distributed equally, isn't it? For that reason we use fluid in these devices, hydraulic lift and hydraulic brake. Okay, in a hydraulic lift, as you can see that in the figure. So in case of this hydraulic lift, as you can see in this particular figure, the two pistons are separated by the space which is filled with a liquid. So this is the liquid. A piston of a small cross section A1. So this is the piston of a small cross section, that is A1, is used to exert a force, that is F1, directly on the liquid. So this piston, it used to exert a pressure on this liquid. That force is given by F1. Okay, the pressure P by in case of that first piston is given by F1 by A1, isn't it? Yes, and it is transmitted throughout the liquid to the larger cylinder attached with the larger piston of area A2. Okay, when we press this piston, that pressure is transmitted to this also, the larger piston having the area A2, which results in an upward force that is given by P cross A2. Therefore, the piston is capable of supporting a large force. Okay, large weight, say a car or a truck placed on the platform. In that case, that force is equal to PA2, where P is given by F1 by A1 into A2. So this one you can see here. By changing the force at A1, the platform can be moved up and down. Okay, based on that pressure, using that pressure concept. Thus, the applied force has been increased by a factor of A2 by A1, and this factor is the mechanical advantage of the device. Okay, by changing the pressure, means at the piston A1, having the area A1, we can apply the pressure, and based on that pressure a force is created at the piston A2, that is given by PA2, and we can move that car up and down based on the pressure. It depends on that applied pressure at A1. Okay, so here we are utilizing that pressure, that Pascal law of fluids, because that pressure, it is distributes uniformly throughout the fluid. That principle we are using in this particular example, isn't it? Yes. So now let us study what is Archimedes principle. Okay. See, fluid appears to provide partial support to the objects placed in it. We have observed it here. Whenever we place an object in the fluid, it gives partial support, not complete support. But solid, it provides complete support, isn't it? So when a body is wholly or partially immersed in a fluid at rest, the fluid exerts pressure on the surface of the body in contact with the fluid. Okay, whenever we immerse any body in the fluid, that fluid, it exerts pressure on the surface of the body, isn't it? In contact with the fluid, which is in contact with the fluid. The pressure is greater on lower surfaces of the body than upper surfaces, as pressure in a fluid increases with depth. Okay, at the lower surface, the pressure is greater. The resultant of all forces is an upward force called buoyant force. The resultant of all the forces which is acting on that body immersed in a fluid acts upward, that is called as buoyant force. Okay, suppose that a cylindrical body is immersed in the fluid, the upward force on the bottom of the body is more than the downward force on its top. Okay, the fluid exerts a resultant upward force or the buoyant force on the body. That buoyant force is equal to, you know how much? That buoyant force is equal to P2 minus P1 into A. This is the buoyant force. So we already know this equation, isn't it? This is P2 minus P1 into A is equal to rho GH, where rho is the density, G is the acceleration due to gravity, and H is the height. Okay, here it is rho GHA. So now HA is the volume of the solid and rho HA is the weight of an equivalent volume of the fluid. So in this particular equation, HA is volume of the solid, means which is immersed in this fluid, and rho HA is given by the weight of an equivalent volume. We call it as weight of an equivalent volume. Okay, and this weight we can write it as P2 minus P1 into A is given by mg, isn't it? Thus, the upward force exerted is equal to the weight of the displaced fluid. The result holds true irrespective of shape of the object, and here cylindrical object is considered only for convenience. Okay, this is Archimedes principle. For totally immersed objects, the volume of the fluid which is displaced by the object is equal to its own volume. So whenever we immerse a solid in a fluid, it will displace some of the fluid, isn't it? So that the volume of that fluid which is displaced will be equal to its own volume. That's what the Archimedes principle says. Okay. Volume of the fluid displaced by the object is equal to the volume of that object. Okay. If the density of the immersed object is more than the density of the fluid, then the object will sink as the weight of the body is more than the upward thrust. Okay, if the density of that object is greater than that density of the fluid, then that object will sink in that fluid. If the density of the object is less than that of the fluid, it floats in the fluid partially submerged. To calculate the volume submerged, suppose the total volume of the object, we if we take it as Vs and part Vp of it is submerged in the fluid. Okay, in order to find the volume which is submerged, you just consider the total volume of that object is given by Vs. And volume of it is only which is submerged. If you consider that volume, in the fluid, then the upward force which is weight of that displaced fluid is given by rho 1 g and Vp, which must equal to the weight of the body. So we can write rho s G Vs is equal to rho 1 G Vp, isn't it? In other words, we can also write rho s by rho 1 is equal to Vp by Vs. Okay, the apparent weight of the floating body is 0. And this principle on a whole we can summarize as the loss of weight of a body submerged, that can either partially or fully, in a fluid is equal to the weight of the fluid displaced. That's what the main principle of Archimedes. The loss of the weight of a body which is submerged in a fluid is equal to the weight of the fluid which is displaced. Okay.